Hello everyone. Today we will manually implement Sigmoid function, cost function, and gradient descent. It will help us to implement logistic regression manually from scratch without using any built-in machine learning libraries. The goal is to understand the mathematical foundation behind logistic regression. It all starts with understanding the problem. Logistic regression is used for binary classification problem where the output is either 0 or 1 and the model first computes a linear equation which is then applied a sigmoid function to convert it into a probability. So let's start with implementation of sigmoid function. So the sigmoid function converts any real number into a value between 0 and 1 as the probability always lies between 0 and 1 and the following piece of code is used for the implementation of sigmoid function, which start with defining the sigmoid function. And here, np.exponential of minus z computes the e raised to the power minus z. Here, if z is very large positive, then exponential of minus z becomes very small, which tends to the output close to 1. And if z is very large negative, then exponential of minus z becomes large, which tends to the output close to 0. This makes it perfectly best for probability estimation. Then comes the implementation of cost function or binary cost entropy. Here, logistic regression does not use mean squared error. Instead, it uses loss, log loss or binary cost entropy. The implementation of cost function starts with defining a function named compute cost, and it takes four parameters of x, y, weight, and bias, where x denotes input features, y denotes actual labels, weights are model parameters, and biases are the intercept terms. The purpose is to measure how wrong our model currently is. Then here, m is the number of training examples. We need this because we want to calculate average cost, not the total cost, and dividing by n ensures the cost is normalized and not dependent on dataset size. Then we compute the linear equation. Here np dot x comma weights multiplies features matrix with weight vector and plus bias shifts the decision boundary. This is the raw output before applying the sigmoid. Then next, we convert the linear output into probability. In this step, h is equal to sigmoid z. Now, each value is between 0 and 1. This makes it suitable for classification. Then comes the core formula, which is binary cross loss entropy formula. Here it is being divided into two parts where at first if the actual value tends to 1, which means if actual label y tends to 1, then it becomes log of predicted probability, where if prediction is 0.9, then the log of 0.9 is being considered, which is a small negative value which is being considered as a small loss. And if prediction is 0.1, then the log of 0.1 is being considered, which is a large negative value which is considered as a high loss. So, wrong confidence prediction increases loss. The next part consists of actual label as 0, where if actual label y is equal to 0, then it becomes log of 1 minus predicted probability, where if prediction is 0.1, it is considered as good prediction. which is a small loss. If prediction is zero point 0.9, it is considered as a wrong prediction, which is a huge loss. So this function heavily penalizes confident wrong predictions. This is why it is better than mean squared error for classification. Then comes the implementation of gradient descent. Here, gradient descent minimizes the cost function by updating the weights. So it's all start with defining a function named gradient descent, and it takes the following parameters of x, y, weight, biases, and two new parameters of learning rate and iteration, where learning rate controls the set size, while iteration numbers is the number of updates. Here the goal is to minimize cost. Then similarly, m is considered as number of training examples which is needed for averaging gradient. Then we use as for loops. Here we repeat updates multiple times. Each repetition improves weight slightly. This is iterative optimization. Then next step computes prediction using current weights. Here these predictions are compared with actual values. And then next comes the derivative of weights and derivatives of biases, where it computes gradient with respect to weights and with respect to biases. Here dw tells us how much to change with uh, how much to change each weight, and db tells us how much to change each biases. Since bias affects all samples equally, we sum the errors. Then in next step, it is considered as the heart of gradient descent. Here we move weights in opposite direction of gradient, as gradient shows direction of increasing cost, and our aim is to reduce cost, so we move in the opposite direction. Here learning rate controls how big the step is. In next step, we monitor the cost. For example, for every 100 iteration, we print cost. And here, if the cost decreases, model is learning correctly, and if cost increases, learning rate may be too large. In the implementation of the gradient descent, the learning rate controls the step size, where small learning rate is considered as slow but stable learning, while large learning rate is considered as fast but risky learning. Then comes the initialization of parameters, where we start with zero weights. Then we gradually adjust them using gradient descent. Iteration defines how many times we update the parameter. Then comes the training of model, where at first the cost is considered high, but as iteration increases, weight improves, cost decreases, and model becomes better at classification. Then comes the prediction function, where if predicted probability is greater or equal to zero point 0.5, then it is being classified as 1. Otherwise, it is being classified as 0. Here, zero point 0.5 is the decision threshold. So we have seen the workflow, which starts with a linear combination or linear equation. Then on this linear equation, we apply the sigmoid function. Then we compute the loss function and gradient function. Then we update their weights. And we repeat this until conversion takes place. Logistic regression models the probability of a binary outcome using the sigmoid function, and it minimizes binary cross entropy loss using gradient descent, where weights are iteratively updated in the direction, and that reduces the classification error. So today we have learned how to manually implement the sigmoid function and cost function along with the gradient descent. Thank you.